In January 1432, a Scandinavian village north of Uppsala endured temperatures so brutal that livestock froze, standing in their stalls. The Baltic Sea turned to ice thick enough to bear merchant carts. Yet every morning, villagers walked to their stone-lined wells, lowered their buckets, and drew up water as liquid and clear as it had been in summer. No ice, no frozen rope, no shattered bucket stuck to a block of solid water. Meanwhile, your modern well engineered with galvanized steel, electric pumps, and PVC piping turns into a useless ice sculpture the moment the thermometer drops below zero. What did medieval peasants understand about water, earth, and coal that we've completely forgotten? Medieval wells weren't shallow pits. They were engineering projects that required weeks of labor, often descending 30, 40, even 60 feet into the earth. In England's Yorkshire Dales, stone-lined wells from the 1300s still exist, many reaching depths of 50 feet or more. This wasn't accidental. Medieval builders understood something fundamental. The earth itself is a thermal battery. Below the frost line, the depth at which ground temperatures remain stable year-round, the earth maintains a consistent temperature between 45 and 55 degrees Fahrenheit, regardless of surface conditions. In northern Europe, the frost line sits between 4 and 6 feet deep. In Scandinavia and Russia, it can reach 8 feet. Medieval well diggers didn't stop at the frost line. They went deeper, much deeper, ensuring that the column of water in their wells remained in contact with earth that never experienced freezing temperatures. Modern shallow wells, by contrast, often sit just below the water table, sometimes as shallow as 15 or 20 feet. Worse, modern drilling techniques create narrow boreholes that minimize contact between water and the surrounding earth. A 6-inch PVC casing surrounded by gravel doesn't transfer heat the way a 3-foot-wide shaft lined with fitted stone does. The medieval well functioned as a massive heat exchanger, with yards of stone surface area pulling warmth from the earth and transferring it to the water column. Your modern well is a thermal orphan, isolated from the very ground that could keep it from freezing. The numbers bear this out. A well that reaches 40 feet deep in northern Europe keeps its water at approximately 48 degrees Fahrenheit year-round. Even if the surface temperature drops to minus 40 degrees Fahrenheit, the temperature gradient through the earth means that water more than 6 feet down never sees freezing. The deeper column acts as insulation, protecting the upper water from surface cold. Medieval wells, with their greater depth and stone-lined construction, maintained this thermal advantage even in the coldest winters recorded in European history. Walk past any surviving medieval well, and you'll notice the construction. Fitted stones, often limestone or granite, carefully shaped and stacked without mortar in the oldest examples, or with lime mortar in later periods. This wasn't just structural necessity. Stone has a specific heat capacity, roughly 5 times higher than air, and significantly higher than modern well casings made of steel or PVC. This means stone absorbs and releases heat slowly, stabilizing temperatures inside the well shaft. A stone-lined well 40 feet deep contains thousands of pounds of rock in direct contact with both earth and water. During summer, this stone mass absorbs heat from the ground. During winter, it releases that stored heat gradually, acting as a thermal buffer. The process of slow stone doesn't heat or cool quickly, which is exactly the point. Rapid temperature changes cause freezing. Slow, stable thermal exchange prevents it. Medieval builders also understood moisture management in stone. Limestone, common in well construction across France and England, is slightly porous. This porosity allows minimal moisture exchange between stone and surrounding earth, which prevents the stone itself from frost heaving or cracking. Granite, used in Scandinavian and Scottish wells, is denser and less porous, but has excellent compressive strength, maintaining structural integrity even when the surrounding ground freezes and expands. Modern wells encase water in materials chosen for cost and ease of installation, not thermal properties. A steel casing conducts heat rapidly, which sounds beneficial until you realize it works both ways, pulling heat out of the well just as efficiently as it might pull it in. PVC is an insulator, which prevents heat exchange entirely. Neither material provides the thermal mass and gradual heat transfer that stone delivers. The medieval well was a living thermal system. The modern well is a static pipe. Medieval wells were wide. Excavations at abandoned medieval village sites in England reveal well shafts 3 to 4 feet in diameter, occasionally larger. The well at Carisbrooke Castle on the Isle of Wight, built in the 1150s, measures nearly 12 feet across at the top. This width served multiple purposes. It made digging and maintenance easier, allowed for larger buckets, and accommodated the rope and windlass systems medieval communities used. But the width also created a massive reservoir of water that resisted freezing through sheer volume. Water has a high specific heat capacity, meaning it takes substantial energy to change its temperature. A column of water 3 feet wide and 40 feet deep contains roughly 1,700 gallons. Freezing that much water requires extracting an enormous amount of thermal energy. Even in severe cold, the surface might develop a thin ice layer, but the bulk of the water below remains liquid, protected by the volume above it and the earth around it. Modern wells, drilled to 6 or 8 inches in diameter, contain a fraction of that volume. A 6-inch well 40 feet deep holds only about 70 gallons. Less water means less thermal mass, which means faster freezing. The narrow column acts like a thermometer, responding quickly to temperature changes rather than resisting them. The width also affects airflow and evaporation. A wide well shaft contains a substantial column of air above the water. In winter, this air column stratifies cold air sinks, but only to a point. The water surface itself releases minimal moisture into the air above it, and the confined space of even a wide well limits evaporative cooling, which would lower water temperature further. Medieval wells often had covers, wooden lids, sometimes thatched roofs that reduced air exchange and prevented wind from reaching the water surface. This simple addition cut evaporative heat loss significantly. A medieval well wasn't just a hole with stone walls. It was an interface between two vast thermal systems, the water column and the surrounding earth. A construction method maximized this interface. Diggers excavated the shaft, then lined it with stone fitted tightly against the earth walls. In some cases, particularly in clay soils, the stones were set directly into the earth without any gap. In rocky ground, small stones or clay packed the space between the fitted well stones and the surrounding ground. This tight fit created continuous thermal contact. Heat flowed from the earth stable at Y-52 degrees Fahrenheit at depth through the stone into the water. The flow rate wasn't fast, but it was constant. Over days and weeks, this steady heat input counteracted the cooling effect of surface temperatures, even extreme ones. Modern wells create thermal breaks. The drilling process leaves a gap between the casing and the surrounding earth, often filled with gravel for structural stability and to prevent soil collapse. Gravel is a poor thermal conductor compared to solid stone or packed clay. The air spaces between gravel particles act as insulation, reducing heat transfer from earth to well. Some modern wells use bentonite clay seals, which help, but the overall thermal connection remains weaker than the continuous earth to stone to water contact of medieval construction. There's also the matter of surface area. A stone-lined well with irregular hand-fitted stones has far more surface area than a smooth PVC or steel casing of the same diameter. More surface area means more contact points for heat transfer. Medieval builders weren't thinking in terms of heat transfer coefficients, but their construction methods accidentally optimized for exactly that. Medieval wells used organic materials, hemp rope, wooden buckets, sometimes leather. These materials seem primitive compared to modern nylon rope and galvanized steel buckets, but they had thermal advantages. Wood and hemp don't conduct heat efficiently, which means a wooden bucket sitting in 48-degree water doesn't chill the water around it the way a metal bucket does. When you lower a metal bucket into cold water, it acts like a heat sink, pulling warmth from the water immediately around it. Do this repeatedly in freezing conditions, and you create circulation that mixes cold surface water downward. Wooden buckets also sealed differently. Medieval bucket makers used swelled wood construction planks held by iron hoops that tightened when the wood absorbed water. This created a seal, but not a perfect one. The slight gaps allowed minimal water exchange between the inside of the bucket and the well, reducing the mixing effect. Metal buckets, especially modern ones with tight seals, displace water forcefully when submerged, creating turbulence that mixes the water column. Hemp rope, thick and flexible, didn't cut into stone well edges the way modern synthetic rope can. This matters because damaged well edges allow surface water and surface cold to enter the well through cracks and gaps. Medieval wells maintained structural integrity longer, partly because the tools used to draw water from them didn't damage the structure itself. There's also draw frequency. A medieval village might have a dozen families drawing from one well, but each family drew water only 2 or 3 times daily. Modern wells, especially those with electric pumps, cycle frequently, pulling water up and creating flow patterns that can bring cold surface influences deeper into the well system. Many medieval wells included structures above them. The simplest was a wooden cover or lid, but larger wells had dedicated buildings, well houses with stone or timber walls and thatched roofs. These weren't decorative. They were functional thermal barriers. A well house creates a microclimate. Even an unheated structure blocks wind, which is critical in preventing evaporative cooling. Wind across an open well surface accelerates evaporation, which requires energy that comes from the water itself, lowering its temperature. A simple roof and walls reduce wind speed to nearly 0 at the well opening. The structure also traps air. Cold air is denser than warm air, but in an enclosed space, even a minimal temperature difference creates stratification. The air inside a well house, even if only a few degrees warmer than outside air, settles in layers. The coldest air would sink toward the well opening, but without wind to mix it. It simply sits there, creating an insulating layer between the frigid outside air and the well shaft itself. Some medieval wells used removable wooden covers fitted directly over the well mouth. These covers, often several inches thick, provided direct insulation. Wood is a poor conductor of heat, and a thick plank sitting atop the well shaft blocked cold air from descending into the well. In extreme cold, some communities added straw or hay over the cover for additional insulation. Modern wells often have minimal above-ground protection. A concrete well cap or a simple metal cover provides structural protection from debris, but offers almost no thermal barrier. The wellhead is exposed directly to ambient air, wind, and precipitation, Some modern systems include heated well caps or heat trace cables, but these require electricity, a resource medieval communities lacked entirely, yet managed to keep their water sources liquid regardless. Medieval communities understood that well water had seasons. In late summer and early autumn, well water reached its warmest, sometimes 55 degrees Fahrenheit or higher in shallow wells, cooler but stable in deeper ones. This warmth represented months of accumulated heat from the earth. As winter approached, the water cooled gradually, but it cooled from the top down and very slowly. The key insight was that the thermal mass of the earth surrounding the well didn't respond immediately to surface temperature changes. When the first frosts hit in October or November, the ground around a 40-foot well was still holding heat from summer. It would take weeks of sustained cold for that heat to dissipate. And even then, the deepest sections of earth never reached freezing. Medieval well users didn't fight this cycle, they worked with it. They knew that water drawn in December would be colder than water drawn in September, but they also knew it would never freeze in the well itself. They didn't expect consistent temperature. They expected consistent liquid state, which is all that mattered for survival. Modern expectations are different. We expect our wells to deliver the same temperature water year-round, and we've built systems that try to force that consistency. Electric pumps, insulated pipes, and heated well houses all attempt to eliminate seasonal variation. But these systems are fragile. They depend on electricity, on mechanical parts that can fail, on insulation that can degrade. Medieval wells had none of these dependencies. They simply existed, using nothing but depth, stone, and earth to maintain function. Today's wells freeze for predictable reasons, all related to decisions made during design and installation. Shallow drilling saves money, but puts the water source close to surface cold. Narrow casings reduce drilling costs, but minimize thermal mass and earth contact. Plastic and metal casings speed installation, but provide poor thermal buffering compared to stone. Above-ground wellheads remain exposed, creating direct pathways for cold air to reach the water. Many modern wells also include pumps and piping that create additional vulnerability. A submersible pump sits in the well, but the pipe leading from it to the house runs through shallow ground or even above ground in some installations. These pipes freeze easily, cutting off water access even if the well itself remains liquid. Medieval systems had no pipes, just a bucket on a rope, manually drawn. There was no secondary system to fail. The electrical dependency creates another failure point. When power goes out during winter storms, exactly when freezing is most likely, heated well caps and heat trace cables stop working. The well becomes vulnerable precisely when it needs protection most. Medieval wells needed no power. Their protection was structural, passive, built into the design itself. There's also maintenance knowledge. Medieval communities maintained their wells communally. Everyone knew how they worked, how to repair stone walls, how to keep the windlass functional. Modern well owners often don't even know where their well is located, much less how it functions or how to protect it. The knowledge gap creates vulnerability. What medieval wells demonstrate isn't primitive technology, it's sophisticated passive design. Every element of the well worked with natural physical principles rather than against them. Depth leveraged the earth's stable temperature. Stone provided thermal mass and gradual heat transfer. Width created volume that resisted temperature change. Covers blocked wind and evaporative cooling. The whole system functioned as an integrated thermal design, protecting water without requiring any energy input beyond the manual labor of drawing water. This approach, designing with natural systems rather than fighting them, appears throughout medieval technology. Root cellars stayed cool in summer using earth insulation. Stone buildings stayed warm in winter using thermal mass. Food preservation used salt, smoke, and drying instead of refrigeration. These weren't compromises or second-best solutions. They were appropriate technologies that worked reliably because they aligned with physical reality rather than attempting to overcome it through energy-intensive brute force. Modern engineering often does the opposite. We identify a problem, wells freezing, and solve it with energy. Electricity for heaters, pumps to keep water moving, insulation to block heat transfer. These solutions work, but they're fragile. They require continuous inputs. They have failure points. Medieval solutions, by contrast, were robust. A stone-lined well 40 feet deep would function the same in its 100th year as in its first, requiring no inputs except occasional stone repair. The medieval well represents a different approach to surviving cold. Depth instead of heating, mass instead of insulation, passive design instead of active intervention. A well 60 feet deep, lined with fitted stone 3 feet wide, and covered with a simple wooden roof would resist freezing at -40 degrees Fahrenheit, using nothing but the Earth's stable temperature and the thermal properties of water and stone. These wells weren't products of ignorance or primitive engineering. They were solutions developed over centuries, refined through countless cold winters, proven by the simple fact that communities survived in climates that would challenge modern infrastructure. Your well freezes because it's shallow, narrow, thermally isolated, and dependent on systems that fail when you need them most. Medieval wells didn't freeze because they were designed around permanent physical principles: earth temperature stability, thermal mass, heat transfer through continuous contact. The knowledge wasn't written in engineering textbooks. It was embedded in construction methods, passed from builder to apprentice, proven every winter when villagers drew liquid water while the world above ground turned to ice. That knowledge still works. The wells that remain still function. The principles haven't changed. We've simply stopped building with them.